And the first thing is that a sequence is an ordered list of numbers. Crucial here. This is crucial. That if you're not confident with what a sequence is, then talking about and doing problems revolving around sequences is not relevant. Okay, and then a series would be the sum of the numbers in that sequence. So it's like you've got this list. The series is then add up the values on the list. We're specifically going to be looking at infinite sequences and infinite series. So what is an infinite sequence? It's a list, and how long is the list? Just keeps going, right? So there's no end to the list. An infinite series then is when you're adding up the terms. Likewise, you're adding up the terms of an infinite list. But we're going to talk about sequences first. So this is the notation for a sequence. That's A sub n, or AN. When you see it in braces like that, that means a sequence. So you may also see it as the list. So what is n? N is the index. It's telling you which one in the list it is. Is it the third in the list? Well, that's A3. That's the third value in the list. Is it A24? That's the 24th value in the list. So A sub n is the nth term in the sequence, or in the list. That's what I just said. So I should have braces around this. So what is A sub 2? He said 3. You agree with that? Yes. A sub 2 is the value 3. It's the second term of the list, or the second term of the sequence. So A sub 3 is 5. A sub 6 is implied to be 11. Okay. So for those who didn't see that, and those who don't remember, or those who don't remember, we want to find a formula. So what formula using n would generate the nth term of the sequence? So one thing that often helps with this, especially for harder ones, is make a table of values. So we want a formula of n that will give A sub n. It's actually easier to see for the larger values. So 3 gives 5, 4 gives 7, 5 gives 9. So what would we do to n? What mathematical thing would we do to n to get A sub n? So this is all he's saying. This is always 1 less than twice what n was. Do you see that? Yeah, the term of your sequence is always 1 less than double what term it is. So that's 2n minus 1. Okay, so practice these two. The one that's should be really easy, and then one that's somewhat harder. So we're trying to kind of find a formula that would give the series given, sequence given.
Shouldn't they be brackets?
Yep, you're right. It should be. Yeah, so making the table really helps to see the term of the sequence next to the value of n. And sometimes it's a little bit easier to look at some of the terms further down than the first couple terms. And then I'm going to get a drink, put the heads together if you want to work together.
No, I was
Oh, is there a mistake in that?
Yeah.
Three halves. Second one's supposed to be 3 halves. Sorry. First one was supposed to be easy.
Good. I thought that this was going to be a really, really difficult weekend. I was looking at it and I was like, my pattern works for every single number with the exception of
Is that better?
Yes.
So what's the first one? This should be easy.
N plus 1 over n.
Okay, that's what you're all saying? Yeah. First one's easy. Now what about this? So how's the second one coming?
So something over n squared. And it's a negative 1 to the n. But the 3 is 2.
A power that's not something. How would make it so?
Oh, I thought you.
So what if it's n cubed?
Is it negative 2n plus 1 to the nth power over n squared? Negative 2n plus 1, 2n plus 1 being in parentheses times negative 1, or times negative 1 to the nth power.
I'm sorry, but I missed the initial premise here. Yeah. Okay. So just make it n plus 1. The one is must be.
So I think the denominator is easy. What's the denominator? So that should have been easy. Numerator should also be attainable. So 1 gives 3, 2 gives 5, 3 gives 7, 4 gives 9, 5 gives 11. So how do you get 11? So let's just ignore that this, what's that? So how do you get 11 from 5, 9 from 4, 7 from 3? Which is this, yeah. 2 n, so the last few, so it's 1 more than twice what n is, right? So 2 times 5 is 10, 2 times 8 is 9, 2 times 4 is 8, plus 1 is 9, 2 times 3 is 6, plus 1. So 2n plus 1, and so then what's happening with this negative? Every other one is negative. This is called an alternating sequence. Alternating sequence, the sign SIGN alternates. And so how can we have something with n's in it that's going to give us this alternating effect? So Andre got it. Don't give it away. Does someone else get, how do you get an alternating effect as a formula of n? Did you guys get it back there? Did you get it? No? Only Andre got it? No one else? What is it?
It's negative 1 to the n.
Negative 1 to the nth power. By repeatedly multiplying by negative 1, it'll go positive, negative, right? Now that's not the only way to do it. What other kind of thing could give us this kind of alternating effect? Anyone know? What type of function could we caress to get it to give us negative 1, 1, negative 1, 1? What kind of function does that? Alternates. Yeah, so like a sine. So how could we use it? A sine. So another way to do this would be so we think about the sine. So maybe so cosine would be a little bit easier on this one, right? Because look, your cosine is negative 1, and then cosine is 1. So how could we use cosine to do this? Cosine of what? So cosine of what gives negative 1? Pi. Cosine of what gives 1 then? But that's not going to help, right? So thinking about n increasing, right? Thinking about n increasing, the angle increasing. So -1 pi, then 2 pi, 3 pi. See, going up by pi every time. So it would it be n pi? Would that work? So when it's 1 pi, we get -1. When it's 2 pi, we get 1. When it's 3 pi, we get -1. So this works too. So both those will give us this alternating negative, positive, negative, positive. And there may be others as well. We could, yeah, so we could get sine to do this for us, but that would be a little trickier because we'd have to be up here at the top and the bottom of the circle, but we could do it. What's that? When n equals 1, what's the cosine of pi? Yeah.
Oh, yeah.
And that's what we got, right? Yeah. Okay, questions on this? Figuring out the formula. Okay, so then we talk about a sequence is convergent. Sequence is convergent if it gets, so as you continue to include more and more terms, those terms get closer and closer and closer to one particular value. So this is the same as what? Our convergent improper integral, right? We have the convergent, we have the improper integrals. So those, we talked about those being convergent if that integral, if that limit, as a approached infinity, got closer and closer to particular values. So we can say the limit, if the limit as n goes to infinity, so what does it mean? It means the next term in the sequence is always closer to L than the one before. That's what this says in layman's terms. Or so we should say a sub n plus 1 is always closer to an, closer to L than an was. For all n. So you always, as the sequence progresses, you get closer and closer and closer to L. And then you can pick any small amount. So this isn't exactly right. But more than what I just wrote, more than just what I wrote, you can pick any small number, and eventually your sequence will get within that close of L. And then you can pick a smaller number, and eventually there'll be an n that you'll get that close to L. And then you can pick a smaller number. So you can pick as small of a number as you want, and eventually the sequence will get within that distance from L. That's really the definition of the limit. Okay, anything else, and the sequence is divergent. Anything else. So the sequence, the values get really, really big. Or the values bounce around between 1 or 2 or 3 values. So those are all examples of divergent. Convergent means pick as small of a distance from L as you want, and the sequence will eventually get within that distance.
How would you test that?
So yeah, that's where we're going. Yeah. But I think the question you're asking is actually outside the scope of this course. That would be like it'd be an analysis course, right? That'd be like if you were going to study math, then you'd do a class that would be like all the underpinnings of calculus, and you would get into formal definition of limit, which is what I was kind of. What's that?
So, would it still be convergent if it bounced, like, say the limit is 0, if you got like +1, -1.5,
It can it can alternate and be convergent. But what still has to happen is you take any distance from L, any small distance you want around L, the sequence must get within that at some point. And then you can keep making that distance smaller and smaller. So yes, it can alternate into a limit. That's right. Okay, so let's compare sequences to functions. So for instance, so what would be the corresponding function to the sequence 1 over n squared? Very simply, it would be 1 over x squared. Okay, so there are similarities and differences of this sequence to this function. So what's the same? The same is the values that it generates, right? So for instance, if n equals 11, so when n equals 11, A11 is 1 over 121. And that would be the same as what? How would we express that same kind of idea with a function?
G of 11
Right, so
is,
G of 11, right? G of 11 would be that same result, 1 over 121. Okay, here's how so this is what we really want to focus on in terms of them doing the same, is that the limit as n goes to infinity of 1 over n squared is going to be the same as the limit as x goes to infinity of g of x, or 1 over x squared. And we're saying as n gets really, really large and we look at the terms of the sequence, does that converge or diverge? And if it converges, what does it converge to? 1 over n squared.
I think it converges to 0.
He thinks it converges to 0. Agree with that? Does it get as close as you want to 0? And then, so take any small distance away from 0. Will it always eventually get within that small distance and then get closer than that even?
Yes,
Yeah. Because that denominator is just going to get increasingly large, and so the sequence just gets increasingly smaller and as close to 0 as you want. That's the idea. As close to 0 as you want. Just take a big enough n, right? If you want to get closer than the person next to you, then you'll take a bigger n, right? You take a bigger n and you'll get closer to, you get that close. Same thing with this limit. So the limit as x approaches infinity, 1 over x squared, is likewise 0. So this is how we're going to use functions. We're going to use the equivalent function often to test the limit of the sequence because they're the same. So we have a sequence. Does it converge? And if so, what's its limit? Well, we'll look at the equivalent function and then conclude that the sequence converges to the same value that the function converges. All right, what's different about these two? What's different about the sequence 1 over n squared and the function 1 over x squared?
There's no equal sign. One thing does not equal another.
No, we're talking more about the idea of a function versus the idea of a sequence. Is what's different about them? Yeah.
A sequence that one's representing just kind of a specific value within a list.
Okay.
Versus g of x is,
Okay. I think you're on to it.
Is that functions perform some sort of operation on the value, whereas like what he said, 1 over n squared is just a value in the list.
But it's still, I mean, that's still generating the value by the formula. Yeah. Okay. Okay. Yeah, I guess that could be. But we could have a sequence that was giving us amounts. We could have that.
Like, are you just looking for like that the sequence is like the entire pattern of numbers, like all the numbers in a sequence follow like that 1 over n squared, whereas the 1 over x squared is just defined a certain like value by plugging into a number of the formula? Like, is that kind of, if that makes sense? Like the sequence is like the whole like set, whereas like the function is good to just find like one.
Mm-mm. No, that's not correct. What you're saying isn't correct. The function is giving us a whole set of outputs for inputs as well.
Okay.
Yeah.
Do they just have like a different purpose?
No. Okay, so what is this? So if we think about a graph. If we were to graph each of these, right? Yeah, exactly. So values of n only take on the counting numbers, right? And so then what do we get? We only get, so 1, 1/4, 1/9, 1/16. We just get a bunch of discrete points, right? But what about 1 over x squared? Curve. Yeah. So it's continuous, right? It's about discrete points versus that a function then is continuous.
So
1 over x squared.
have to have whole numbers for n.
Yeah, because you're counting the terms of the sequence. Remember what n is. N is like, if n equals 4, you're saying it's the fourth one of the sequence. You can't have a 4.5 term of the sequence, right? So yeah, that's what n is. N is telling us which value of the sequence it is. So now 1 over x squared looks like this. It's continuous except for at 0, because it's undefined at 0. But the domain is all real numbers except 0, whereas your quote-unquote domain of the sequence would just be the counting numbers, because it's telling you which number of the sequence you're at. But the important thing is that the limit is the same, and that's how we're going to use it. That's how we're going to use functions to help us with sequences. The limit as we go to infinity of the discrete points is the same as the limit of the continuous function. Both, in this case, both 0, right? The limit is, the y value is getting as close as you want to 0 in both cases, for increasing n or increasing x. Okay, so common forms of sequences. So we're just going to focus on 1 over n to the r. Don't write down this whole screen and not listen to me. Okay. So 1 over n to the r. So we're asking, in this case, we're asking for what values of r. So examples. 1 over n cubed, or like I just showed you 1 over n squared. 1 over n to the 0.01. 1 over n to the 598. 1 over n to the -1/2. Examples. Those are examples of this form. So the question is, for what values of r does it converge? what do you think? So can we start thinking about intervals of R where for sure it would converge? Like, so what values of R for sure would this converge? And then,
Anything bigger than 1.
okay, so you said anything bigger than 1. R greater than 1. So would we agree that it would converge for R greater than 1? Okay, what about R equals 1? What is that? You'd have 1 over n. Does that converge?
Diverge.
It diverges. Agree? 1 over n. It diverges? So let's write out the first several terms of the sequence 1 over n. Go. What is the sequence? Explicitly write out the sequence 1 over n. But just practice writing it out as a sequence. That's good practice. Okay, so here's 1 over r squared. This is what we talked about in the previous example when we were comparing. So what are we doing? So I'm going to change it to the function 1 over x to the r, right? And so if we're analyzing the limit as x gets really large, we know the results will be the same for 1 over x to the r and 1 over n to the r. So here is the one that we compared. We compared 1 over n squared to 1 over x squared. So here's 1 over x squared, convergent to 0. So what did you come up with for 1 over, when r equals 1? We said divergent. Still think it's divergent? Convergent? So let's try it. So I'm going to put in r equals 1 and see what it looks like. Does it get as close as you want to 0, just as long as you pick a large enough n? That's what we're asking. Does it get increasingly close to 0 and as close to 0 as you want as long as you pick a large enough n? 1 over n, does it? Yeah, sure. Yeah, because your n is going to get really, really, really big, and so that's going to make the fraction really, really small, as small as you want. Just keep picking a larger value of n, and you eventually get to within any tolerance of 0 that you want. Okay, what about values of r less than 1? What about 1/2? 1 over x to the 1 over n to the 1/2. Nope. Just does it converge or not? Yeah.
So the sequence where it was natural log of n would be convergent.
The natural log function continues to increase always.
What was the one we used? I forget. 1 over natural log n was what we used. Whichever one we used as an example where it went to 0 but it didn't go fast enough.
But we're not talking about. All we're talking about does the sequence converge or not? We're not talking about fast enough.
So it has nothing to do with
Nothing to do with that.
Okay.
Nothing to do with speed. Just does it converge or not? So what about 1 over x to the 1/2? You think it's going to converge? Why? So that's like square root, right? 1 over the square root of x.
So although it's the speed, so you said we don't need to care about the speed. So when x goes to infinity, the square root of n, I think still goes to infinity.
Yeah, right, exactly. Good, well said. So when x goes to infinity, the square root of x likewise gets really, really big. So 1 over that is going to get really, really small. So here is 1 over the square root of x. It just not as fast, right? But that's not what we care about right now. We just care about, is it going to converge to 0 or not? Yeah, just slower than 1 over x. Okay, and so, yeah, go ahead.
So just to clarify, if this was like a
We're saying it's a convergent function that's converging to 0.
But when we did like the function, doesn't have to be like go to 0 like really fast.
But all we're saying is it's convergent or not. That's all we're saying. Does it go to 0 or not? That's all we're saying. So you guys are trying to accumulate at that rate, right? So what we were talking about was if this was a rate function, and we were going to accumulate at that rate indefinitely, would the accumulation level off, or would the accumulation just get really, really big? Well, that depends on the rate of the rate, if the rate is getting down fast enough or not. Now, all we're talking about here is, does the function converge to a value or not? We're not talking about rate versus accumulation anymore. Does that help? Yeah. Okay. So really, all it has to be is, so here's point 1. So now I'm going to zoom out on the x-axis, and we'll see what happens. Does it converge or not? So this is 1 over x to the point 1. Is it going to converge to 0, or is it going to? Yeah, it's just going to take really big values of x, right? So now we're in the what? We're in the 10 millions here. Now we're getting to the billions. Trillions would be 10 to the 12th. So now these are the trillions.
Clear defined space.
But you never run out of x values, right? So your x is as big as you want. You're going to take the 10th root of it. The 10th root of it is going to eventually become a super large number because you're never going to run out of big numbers of x. So the 10th root of it will still get really, really big. It'll just take a lot longer time to do it, but that we don't care about that now, right? We don't care about that.
What's up with trillions?
So quadrillions. So you see, you can see we're up in the quintillions and quadrillions, and it's finally feeling close to 0. Okay, so what is our rule then? So R just has to be what in order for this to converge? Greater than 0. So we say that 1 over n to the r approaches 0 as n gets really large if r is greater than 0. That's all we need. Now remember, if this was a rate function and we're talking about the accumulation, what does r have to be for the accumulation to level off to a finite value? Or what? What does that have to be? Remember? Greater than 1, right? That was the greater than 1 thing. If this was some accumulation function, then if r was greater than 1, or sorry, rate function. If r was greater than 1, the accumulation would level off. Okay, p to the n. So p to the n would be things like, what would that be? That'd be things like 2 to the n, negative 10 to the n, 0.4 to the n, negative 3/5 to the n, negative 7/8 to the n, etc. So for this one, we're asking 1 to the n. For what values of p will p to the n converge to a finite value? Why? So he's throwing out between negative 1 and 1. What about 2 to the n? Will that converge? Is that going to converge? 2 to the n? That's right. What is that sequence? Write it out. First term is 2. Second term? 4. Next term. 8. Convergent sequence. Badly divergent, right? I mean, this is just going to accelerate to infinity, right? Because we keep multiplying the last one by 2. Divergent, right? What about negative 10 to the n? Yeah, even worse, right? Half the terms are going to be getting really large positive. The other half of the terms are going to be getting really large negative, right? So it's going to. So this is even worse divergent. What about 0.4 to the n? So 0.4, 0.4 squared. So you always keep in mind what you're thinking about, that this is a list of values, and what is that list going to do? 0. You're always taking 40% of what you had before, right? You're always taking 40% or 0.4 times the previous term, because you're going to multiply by 1 more 0.4. Convergent? Yeah, this is going to converge to 0, right? Because you're just going to keep reducing it by a fraction of 0.4 of what you had before. Negative 7/8. Convergent? So you're taking 7/8 of what you had before, but it's going to be what? It's going to alternate negative, positive, negative, positive. Convergent? So this is the example that, was it Jacob who brought this up? The alternating one. Jacob, yeah. So Jacob brought up this idea. Can it converge if it's alternating between negative and positive? Yes, as long as it's getting closer and closer to a particular value. That's what happens here. So you're gonna, by multiplying by 7/8, you're always taking a fraction of what you had before, and then you're just gonna have an alternating effect, negative, positive, negative, positive. So what will that look like? That's an exaggerated view of this, okay? If you were to graph the sequence. So that will converge to 0. So you're honing in on 0. Okay, what about 1 to the n? Convergent? 1 to the n. What is that sequence? What's 1 to the n? 1, 1, 1, 1, 1, 1. Convergent? Does it get as close as you want to a particular value? Yes. It's 1, right? It's convergent to 1. So that's the one exception. So what Andre said was right. It goes to 0 as long as p is between negative 1 and 1. But then it also goes to, there's another case where it will approach 1 if what? P is 1. What about if p is negative 1? What sequence do you get? If p is negative 1, we get negative 1, 1, negative 1, 1, negative 1, on and on and on. Convergent or divergent? Can it be convergent? That's the question. Can it be convergent to 2 values? No. Single value. Has to hone in on getting exceedingly close to one particular value. This is divergent. This is divergent. Doesn't get close to one particular value, one limit. So this is how it's convergent. Okay, so we've got these two basic sequences, like forms of sequences, 1 over n to the r and p to the n. And then, so now you're going to be analyzing sequences for convergent or not. There's other things that you have to consider. So Here's some other strategies. Consider the associated function. Just list out the first several terms. Often you can reason just from that. We need algebra and pre-calc knowledge, okay? And then some common sense. So there's like no, they're all kind of different. These problems they're all a little bit different. So it's got kind of like we have a bunch of tools and we apply the right tool at the right time. So here's a list of them. So can you apply the 1 over n to the r? Can you apply p to the n? Can you do some algebra on it to get it in one of those forms? Okay. Let's just see how you do. Work on it. Get as many of these as you can. The question is, so what's it? You're gonna write out the first 3 terms to practice what they each mean, and then you're gonna try to analyze and decide if each one is convergent or not divergent, and if convergent, to what limiting value. So do as many as you can.
Is it correct to say because it oscillates? Divergent because it oscillates?
Maybe you might need a little more than that.
Just say it's convergent because it oscillates. One, it goes to.
You're doing the first one?
Yeah.
You don't need, there's a very straightforward explanation to why the first one is divergent.
Just goes to negative infinity, positive infinity.
It's going to be an approximation. You would express those terms exactly, not decimal approximations. How do you express this when n equals 1? It's that value when n equals 1. Yeah? I couldn't hear you? So we want to express these exactly, not decimal approximations. How do we express these terms exactly? How do you express the term, say, of this one here exactly, not decimal approximations? What?
If they're radicals, you have to know like when it's like rad 2.
No, I'm just saying, how do we list this out so we have the exact values of the terms? What is it? Right. And then what's the next one?
4 bits.
And then? 9/20ths? Like that? Okay. That's self-explanatory, right? Do I need to keep doing writing out the first 3 terms? Is that pretty? So that should be easy, but it's the mindset that you have when you see a sequence. That's why I'm asking you to do that, writing out the first 3 terms, because the mindset is when you look at each of these, you see those, you think a list. You think a list of terms, a list of values. Okay, so now convergent or divergent? First one. Divergent because?
Goes up and down.
Those
Half of
goes
the
to 0 to
Okay, so but we want to identify what this is though. Because we've already kind of had that conversation. What do you have? What kind of sequence? No, this was our p to the n, right? So you want to invoke these things that we talked about, right? So you want to say, this is a p to the n sequence, and p is -4. It's not between -1 and 1. It's -4, so it's divergent. So it's great that you want to think about, you know, why does that diverge? That's great. You know, yeah, because it's positive and negative, and those are both increasing, getting more positive and more negative. Clearly, it diverges. We also want to look for patterns of forms that we've talked about, and invoke that. So this is p to the n. P is -4, which would be divergent. Okay, so these two are kind of similar in that we have to analyze this ratio. There are two ways to analyze. There's two ways to analyze, say, n squared over 3n squared minus 7. The first is you think about your pre-calculus. This is a rational function, and we looked at like horizontal asymptotes of a rational function. As n gets very, very large, what does it do if the degree of the numerator is the same as the degree of the denominator? Remember this from pre-calculus?
Oh, it will be equivalent to their 1/3.
Yeah, the ratio. So the ratio of the leading coefficients. If your degrees are the same, and you let n get very, very large, this is going to approach 1/3. Right? This is going to approach 1/3 as n gets really large. Therefore, the sequence approaches what? Therefore, the whole sequence will approach what? Sine of 1/3. So if inside is getting infinitely close to 1/3, then the whole sequence is getting infinitely close to whatever the sine of 1/3 is. So this is convergent to the sine of 1/3. So that's one way to analyze a ratio, like a rational sequence like that. Is you invoke what you learned in pre-calculus about rational functions and horizontal asymptotes. The other way to do this is you can divide top and bottom by the highest power of n. So what is the highest power of n that we see? N squared. So we can do n squared, divide the top and bottom by n squared. So 3n squared over n squared minus 7 over n squared. And we get sine of 1/3 minus 7 over n squared. And now let n get really, really large. Right, because when n gets, we know exactly what this is. We get 7 over n squared. That's our 1 over n to the r, right? And that's 0 if r is greater than 0, and it's 2. So this goes to 0 as n gets really, really big, and so the whole thing goes to sine of 1/3, which is the same conclusion we had before. Okay, so looking at this one now, up here. Again, we have a rational function, right? So now what's the degree of the numerator is bigger than the degree of the denominator. What does that mean as n gets really, really big? So this degree to the 4th is bigger than n cubed. It'll just get really, really big, right? Because n to the 4th, when n is very large, n to the 4th will dwarf n cubed, right? When n is 1,000,000, n to the 4th is 1,000,000 times greater than n cubed. When n is 1,000,000,000, n to the 4th is 1,000,000,000 times bigger than n cubed. And that just keeps getting worse and worse. So looking at it as a rational function, that whole thing gets very, very large because the degree of the numerator is greater than the degree of the denominator. And what about the square root of that then? Yeah, the square root of a number that gets increasingly large gets increasingly large. So this is divergent. Divergent. Okay, what about n to the minus 4? 1 over n to the 4th. Convergent or divergent? Converges to 0 because 4 is greater than 0, right? This is 1 over n to the r. You recognize that that's 1 over n to the r. As long as r is greater than 0, boom, it converges. What about this one? 1 over square root of n. Same as 1 over n to the convergent or not? Yes, r is greater than 0. Convergent to 0. How about this one? Anyone get this one? Pi to the n over 3 to the n is?
Divergent.
Because?
Because pi 2 is bigger than 3.
Okay, can we apply something else? We rewrite this as?
Oh,
P to the n divided by n.
No, we want p to the n. Can we write this as p to the n? Pi over 3 to the n. And what about pi over 3? What about pi over 3? So does this converge or diverge?
it's bigger than 1, so
Pi over 3 is greater than 1. Therefore, divergent. If p has to be between negative 1 and 1 to converge to 0. But here, p is greater than 1. All right, what about this one?
still converge.
Because it just multiply one third to that one.
Okay, right. Okay, so this brings up the point that when you see exponents, you have to really conceive what you're looking at. What does pi to the n mean? What does pi to the n mean? Can you explain what that means?
Pi times n times. Pi multiplied by itself n times.
So for instance, so yeah, he's got it. What about 8 to the 4th? What does 8 to the 4th mean? 8 multiplied by itself 4 times. You have to imagine this. So therefore, pi to the n is? You're multiplying by pi how many times? N pi's, right? N pi's. And then what about 3 to the n plus 1?
Yeah, it's just 3 times itself, 1 more time than however many times.
Right, so however many number of pi's you have, you're going to have that many 3's. And actually one more. So we can say 3 to the n plus 1 is the same as 3 times 3 to the n. Right? Really important. Because you're multiplying by 3 one more time. So 3 times 3 to the n.
Oh, it's still diverge.
Still diverge because now you're just taking 1/3 of the sequence of all the terms of the sequence you had up here. Right? So it's all the terms of the sequence up here, 1/3 of that. Doesn't matter. 1/3 of something that gets infinitely large is going to get infinitely large. So that's divergent as well. What about this one? Clearly divergent. It's not, you have to get infinitely close to a single value. This never does that. Okay, any questions on, I think I talked about all of them. Any questions about any of these?